And we're back with more modeling of electronic systems. We're going to talk about some more op-amps, and this time it's going to be a non-inverting op-amp. Valerie, it's non-inverting. You didn't get it wrong. Non-inverting. Okay, so here's the basic setup for a non-inverting op-amp. And we have to label our system here. So these impedances, we'll call them Z1 and Z2. And we need to have an input for our transfer function, so that's what we want to define. So our input here will be Vi of t, and that's going into our positive terminal of our op-amp. And then our output is going to be the output here, so Vo of t. And our op-amp, remember, has a gain, we'll call it A. So even if you don't immediately identify this and exactly how it works, we can use the op-amp equation to kind of understand the system. So let's start with that equation. We know that the output of the op-amp, so Vo of t, is going to be equal to some gain multiplier, A, of the voltage at the positive input minus the voltage at the negative, V positive t minus the voltage negative t. Alright, so that's our starting equation. Now let's start filling things in. Out's the same. Our gain is still A. But what's our positive voltage? Look here, I of t. And then what's our negative terminal? Now you have to remember exactly what's happening here. We have a current coming from this voltage. We have current going through here. Well, remember, this is a high impedance input, so current does not flow through it. So all the current will flow through here to ground. If you kind of erase this, ignore these parts, what you'll see is there's a voltage divider here, right? So we want to get this voltage, and we have two impedances or resistances. So we can use the voltage divider equation there. So from this voltage, so we'll start there. Our main voltage at the top of the voltage divider is V out of t. And then we know from the voltage divider equation that the denominator will have the sum of the voltages. So Z1 plus, the sum of the impedances, Z2, and the numerator has this impedance, so Z1. Okay, so there's our base equation. Let's take the Laplace of it. And I'm going to break out the A right here already. And so this would be minus the output, the out of S, A, and Z1 over Z1 plus Z2. Okay, so eventually we want to get our input over our output because we need to look at the transfer function. So let's try to break things apart. So let's move this term over here and separate the terms, so we'll be out of S. And then here we hit a 1. We're adding this part, so plus A Z1 over Z1 plus Z2 equals A B I of S. Okay, so let's move around terms. What we really want, right, is V out of S over V in of S. So if we move that all around with that, okay, we're going to get A, this term, over this term. 1 plus A Z1 plus Z1 plus Z2. So now we have to remember that A is our gain, and in this case our gain we assume to be infinite. So as A goes towards infinity, this 1 can be completely ignored. So we'll take that essentially to 0. And ignore that term, and then we have just an A over an A. So we can cancel those two out and flip this around to get our final expression. So we'll write that here. So our final expression will be P of S equal to this, which is equal to Z1 plus Z2 all over Z1. And like the other op-amp equation, if we know these impedances, say it's a combination of resistors and all the other components, we know the impedance of this branch, we can plug that value into here and go from this expression. So this is a general expression for this non-inverting op-amp structure. And that's how you do the transfer function for a non-inverting op-amp. I just realized that you can't really see this. This was Z2. So just rewatch the video and just pretend that that's there, okay?